Okay, moving right along, if you have zinc nitrate and you add sodium hydroxide to that, you'll get a white precipitate of zinc oxide, zinc hydroxide right here. But if you add more than that, that precipitate will go back into solution. So it's very concentration dependent. Calcium carbonate, that's something a lot of people are familiar with. That's the chalky material that you take as an antacid, neutralize the effects of acid in your stomach. This right here shows SO2, and it exists in this resonance type of form of sulfur dioxide. That's an impurity that is produced in some burning operations and other processes, industrial, where you want to remove it as a pollutant. This right here is sulfur trioxide in the gas phase, and it has 3 separate resonance forms. And what happens is the more resonance forms you can have with something, the more stable that particular product is. So more resonance forms, more stable. So this is a much more stable type of gas than SO2. But this one right here is the one that is the basis for reactions that form sulfuric acid. Here is 2 molecules. This is dichloromonoxide, and this is chloro dioxide, right? 2 very different materials, somewhat the same purpose though. Both of these are extremely good disinfecting and water purification materials. This is the one that is better though for swimming pools. You don't want to consume this one at all in any way, shape, or form. Okay, but so when you have when you talk about the chlorine scent that you get from a pool that's just been treated, this is actually the material that you're actually smelling. This right here is the one that's used for drinking water. It's an antimicrobial, and it forms a chloride ion, and that chloride ion is the one that actually does the antimicrobial activity. Okay, so 2 different ones. This is also a called wood bleach, and this is primarily for swimming pools. This is for actually our drinking water that the municipal drinking water people use. This right here shows nitric acid, okay, and you can see 1 hydrogen atom associated with oxygen here, nitrogen with 3 oxygens around it, and it has these 2 forms right here. If you have the nitrous acid, what that means is you only have 2 oxygen associated with it. And this is orthophosphoric acid, so this is 4 oxygen and 3 hydrogen ones. So you've got 1, 2, 3 hydrogens that can be removed from here. And this is the Lewis structure of that particular one. This is orthophosphoric acid. This is phosphorus acid. Now we only have 3 of them here, and we have 1 of the hydrogens linked directly to the phosphorus. These are the ones that dissociate, these 2 over here, to form the acid. This is the sulfuric acid, and you have the hydrogen associated with 2 of the oxygens, but not with the other 2. And this is the chloride ion, ClO2. Okay, this is what is formed for that one material that I mentioned earlier. This is the chloride ion, which is very good for disinfection. Now you can also have the chlorate ions. Here you've got 3 oxygen and only 1 lone pair. And this right here is a very strong reactor. Perchloric ions is when you have 4 of the oxygens around a single chloride. And this produces perchloric acid, and this is one of the strongest of the different acids. As a matter of fact, the sequence that we knew is this is the strongest of the chlorine, oxygen, or chlorate acids. This right here is less strong, and this is a weak one. Okay, let's talk about sulfur now. Sulfur is that brimstone smell, and they've always associated that with hell, and because volcanic acids produce hydrogen sulfide. And it's a burn when hydrogen sulfide gets hot, it's a very burning to your nose. You don't want to have very much of that at all. It's the 17th most common element in the Earth's crust. And what happens is for the longest time, when people went to provide sulfur, they used the Claus process, which is the desulfur, which is a process the Fraiche process does that. The Claus process is what is used mostly today. This is the one we are processing a lot of natural gas and crude oil. And because of that, a secondary element that is produced is sulfur. And it's called the Claus process, and it's the desulfurization of these materials that is the source of so much. There are places where you can still go in and mine it, and that's the Fraiche process right here. This is for underground deposits. It utilizes it injects material in there. Compressed air goes down, okay, heats it up, and superheated water goes in as well, and that pulls that sulfur, water, and air out in these chambers right here. So that's the Fraiche process. Sulfuric acid is the most common chemical element in the world, industrially. Okay, we produce more sulfuric acid than any other chemical. There's 200 million tons, more than that, produced every year. It's used in fertilizers, explosive, petroleum products, steel, other metal refining operations, dyes, petroleum products. A measure of the industrial strength of a nation in terms of manufacturing ability is number 1, sulfuric acid, and number 2, steel. Number 3 has to do with the plastics, and number 4 has to do with the petroleum that's produced. Okay, so those are the measures of the strength of the economy of an industrial country. And the sulfuric acid is produced through what is called the contact process. That sulfur trioxide that we talked about is reacted with sulfuric acid. I know it sounds strange to think that you're going to produce sulfuric acid by reacting something with sulfuric acid. But you have to add this to this, and it produces this right here, H2S2O7. Okay? And this right here breaks up readily with water to form more sulfuric acid. If you go through the balancing equation, you'll see that you get more sulfuric acid out of it than what you actually put into it. Okay? If you try to do this right here, just adding this directly to water, results in an explosion. So you very carefully use this, react it with sulfuric acid. It produces something called oleum, H2S2O7, and then the oleum is just added to water and it forms sulfuric acid. Let's talk about the halogens, finally. Chlorine is a gas. Bromine is a deep orange. And this is iodine over here. It's sort of a purplish color. Okay? So I remember at the Magnolia plant down there in the Boot Hill, this is what the workers would actually, they would inhale this right here just to prove how manly they were. I don't know how they had any nose hairs left at all when they were breathing this sort of stuff in. This is mercury iodide. When potassium iodide and mercury nitrate are mixed, you get this solid form right here. Underground deposits, sodium chloride, yes, sending somebody to the salt mines has existed since the time of the Romans, and it doesn't get any better. Underneath the entire city of Detroit, you have all sorts of salt mines down there. Underneath some areas around Kansas City, you've got salt mines down there. And in Arkansas, you've got salt mines. So there's a lot of places. This right here happens to be one in Poland, but it's essentially where some of the seas dried up and left behind all of that water. Of course, you can they've got the Great Salt Lake out in Utah where it hasn't quite dried up yet. This right here is IF3, and it has this type of a structure. Then you have IF5, and then you have IF7 right here. And just showing you the different possible structures you can have once you get to the lower level of the iodine materials. We're going to go on now to the transition metals. Now you'll notice that for the transition metals, the reason why we didn't include aluminum there, we used on 3 through 11 in terms of the groups, but not 12. Not 12 as well. 12 and 13 are ones that are where you've got a lot of where you're just filling in on 12 you're filling in an S electron. So anyway, presence, preparation, occurrence, and we're talking about coordination, chemistry, and all of those things. Okay. This right here, the transition metals form very vibrantly colored complexes. You've got the green malachite, the azurite, and the prostite, right? And all of these have different types of metals that they are complexed with. And it's a whole course in and of itself just to say, okay, where do I find these? How do I extract the metals from them? Or do I just polish them up and give them to my girlfriend? So the transition metals are located in groups 3 to 11. And these are the intertransition metals, are in the 2 rows below right here. These are the intertransition down here. But we're going to talk mostly about these up here. Europium is used on display screens for televisions, computer monitors. Here is the transition metals for the first scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Okay, zinc really shouldn't be there. It should only be these right here. This right here is just in that form. But all of these right here, except for this one, have a variety of different transition states that you can see them in, right? And so that means that they have very different salts they can form and different structures that they will have as well. This is a nugget of copper. This is gold right here. And this is iron. Okay. Iron is the 4th most common in the Earth's crust. Copper, that is all the way down to 26. And gold, that is down to 72. Okay. Silver is at 65. And so there's a lot of other ones that are much more prevalent. But there's a fairly limited supply of gold, and gold has been a standard measure of wealth for centuries. Now, this right here is a blast furnace. A blast furnace is used to take iron ore and heat it up with a lot of air, and then what they do is you can have roasted ore and coke and all of that flowing in right here. It floats up here. The slag comes out down here. That will be your coke and your limestone and those things. And so at these different temperatures, carbon plus oxygen forms carbon dioxide. Calcium oxide plus silicate forms carbon monoxide, plus this slag. This right here forms into the slag. And then right here you get these carbonate materials in this. Finally, up here you start getting iron.